This call is now being recorded.
Okay, let us discuss about stress concentration. So, to begin with, you consider you have a pipe like this. Okay, there is a pipe like this with an outlet here and an inlet here. And assume that there is a liquid which is flowing in this pipe, say water. Okay, assume that the flow is laminar. So now what will happen? This water can easily flow through this pipe without any change in direction, right? These arrow marks will indicate the direction of flow of fluid. Basically, since the pipe is having an uniform cross section, the water molecules can easily flow by maintaining its laminar nature of flow. But you consider, suddenly what I will do, I will consider a pipe like this. I will make use of something like a collar and I will reduce the cross section of it. Okay, and I will reduce the cross section of it by a reasonable amount, right? Now what will happen? The water molecules ideally were flowing this way, right? This layer of water molecules is not facing any obstruction, it will easily flow through. Even this layer will easily flow through. But the layers that are above as well as below this cross-sectional area, they have got an obstruction here, right? They have got an obstruction here. So what will happen? The water molecules cannot cross this boundary. Thereby, they will try and accumulate in this vicinity, right? They will try and accumulate in this vicinity, thereby increasing the amount of fluid, that is, thereby increasing the concentration of the fluid whenever there is change in cross section. There is an abrupt change in cross-sectional area of the body. Since there is an abrupt change in cross-sectional area of the body, let me try to redraw it again with a better visibility. So this is the pipe. So whenever there is an abrupt change in cross-section, what will happen? The water molecules here, they will try and get concentrated here. Along with the regular water molecules, this region is facing an increase in the amount of fluid, right? So basically what is happening, the water molecules are getting concentrated in this particular region. Now you imagine the same thing happening in case of stress. You consider this to be a solid body. You consider the blue colored lines to be the lines representing the flow of stress, right? You consider these blue colored lines to be the lines representing flow of stress. Since there is an abrupt change in the cross-sectional area, what will happen? The stress lines, the lines that represent the flow of stress, are getting concentrated wherever there is a change in cross section of the body. Basically what is happening, if there is an increase in cross section, that is not a problem. But here what is happening, there is a decrease in cross section. It means to say that, typically assume that this component is subjected to tension, right? If the component is subjected to tension, the formula to calculate the stress induced is given by F by A, right? The formula to calculate the stress induced is given by F by A. You consider the region here, you consider the region indicated in the red colored line, call this region as A, right? This stress induced at cross-sectional A can be, you assume that the magnitude of force is say 200 Newton. Let the magnitude of force be 200 Newton. Let the area of cross-section at this red colored region be 100 mm square, right? Let the area here be 100 mm square. Now what is the stress induced cross-sectional area A? This is given by 200 divided by 100, which is equal to 2 MPa. Which is equal to 2 MPa. But you consider another region, which I am indicating it in green. Assume that the area here is 50 mm square. Assume that the area here is 50 mm square. Now what will be the, call this cross section as B. Now what will be the stress at point B? This will be 200 divided by 50, which is equal to 4 MPa. Now when you compare these two scenarios, the stress has got doubled. The stress has been increased by twofold, right? There is a twofold increase in the magnitude of stress. Now what is happening? What is the effect of it? There is a very high concentration of stress in this particular region. What I am indicating it in green. So in this green colored region, because of the lack of availability of material to take up the force, there is a sudden increase in this stress. This localization of stress due to abrupt change in cross section. This localization of stress due to abrupt change in cross sectional area is what we call as stress concentration, right? This is what we mean by stress concentration. So artha agidea idu concept. ಈ ಕಾನ್ಸೆಪ್ಟ್ ಅರ್ಥ ಆಗಿದೆಯಾ
ಸರ್? ಇನ್ನೊಂದು
ಪ್ರದ್ಯುಮ್ನ, ಲವ್ ಮೋಹಕ್, ನೀ ಮಧ್ಯ ಯಾವಾಗಲ ಜಾಯ್ನ್ ಆಗ್ಬಿಟ್ಟು ಇನ್ನೊಂದ್ಸಲ ಹೇಳಿ ಅಂದ್ರೆ ಹೆಂಗೋ. ಓಕೆ, ಸೊ ಬೇರೆ ಸ್ಟಾರ್ಟಿಂಗ್ ಇಂದ ಇದ್ದವ್ರಿಗೆ ಅರ್ಥ ಆಗಿದೆಯಾ ಪ್ರದ್ಯುಮ್ನ? ಓಕೆ, okay, fine. So let me just put it in a nutshell. So basically you consider this equation. Let us assume that the component is subjected to a tensile force of 200 Newton. So basically illi enagide, basically this body is having two cross sectional dimensions, right? This body is having two cross sectional dimensions. Just give me a moment. Okay, let me read it again. Okay. So there is a body like this. Here the cross-sectional area of the body was 100 mm square. Now suddenly there is a decrease in cross-sectional area of the body, right? So here in the green colored region, I had called it as B. The area here was 50 mm square. In this red colored region, just give me a moment. The system is quite slow. Just give me a moment, guys. There was some problem. Okay, I think I have lost that slide because the system did not auto save it. Let me just brief it up. Right, this system is a bit slow. There was some problem. So basically we were discussing about stress concentration. Okay, so what we were doing was we had considered a plate whose area had got decreased by a significant amount after a certain length. Okay, this component was subjected to a tensile force F, whose magnitude was 200 newtons, I believe. So here, let me call this as cross section AA. The area here, the area of cross section at cross section A was given to be what? 100 mm square, alva? This was taken to be 100 mm square.
So presentation
Now, in this
ಕಾಣಿಸ್ತಿಲ್ಲ.
red colored region, let me call this region as B. The cross-sectional area at point B was taken to be 50 mm square. This is just for illustration. Now you know the formula to calculate the stress induced in the member when subjected to side versus F by A. ಕೇಳಿಸ್ತಿದೆಯಾ ನಮ್ಮ ಮಾತಾಡ್ತಾ
ಪ್ರೆಸೆಂಟೇಷನ್
ಇರೋದು?
ಕಾಣಿಸ್ತಿಲ್ಲ.
ಸರ್ ಕಾಣಿಸ್ತಾ
ಪ್ರೆಸೆಂಟೇಷನ್ ಕಾಣಿಸ್ತಿಲ್ಲ.
ಸರ್ ಪ್ರೆಸೆಂಟೇಷನ್ ಕಾಣಿಸ್ತಿಲ್ಲ.
Okay, just give me. Audio clear ಇದೆಯಾ?
Yes sir.
ಇವಾಗ ಕಾಣಿಸ್ತಾ ಇದೆಯಾ?
ಎಸ್ ಸರ್.
Okay, fine. Now, see, we know that the formula to calculate the stress induced in a member when it is subjected to tensile forces sigma is equal to F by A. Now, let me try to calculate the same thing in this green colored region. Now, the stress induced at point A is equal to 200 divided by 100, which is equal to 2 MPa, right? Whereas in the red colored region, the stress at point B is 200 by 50 because the area has been reduced significantly. Now, what will be the stress? The stress induced is 4 MPa, right? Now, the magnitude of stress has got doubled, right? The magnitude of stress has been increased by 2 times. Why? The reason is in this particular region, there was material available till this point to take up the force. Now, since there is a sudden change in cross section, since there is a sudden decrease in cross sectional area of the body, there is no material to take up the available force, right? Since there is no material to support the applied force, there is a sudden increase in the stress in that particular region. Now, this localization of stress. Now, what do we mean by localization? Localization ಅಂತಂದ್ರೇನು? ಯಾವುದೋ ಒಂದು particular locality this magnitude of stress is increasing, right? In this particular locality, the magnitude of stress is increasing. So, the localization of stresses due to abrupt means sudden, due to abrupt decrease. Typically, people prefer to use the word change in cross section, but if there is an increase in cross section, then it might not be a problem. So thereby we might substitute the word change with decrease. Due to abrupt decrease in cross sectional area of the body is called as stress concentration, right? So how can we define stress concentration? Stress concentration can be defined as localization of stresses due to abrupt decrease in cross sectional area of the body. So this is what we mean by stress concentration. Artha agidea idu concept ellarguna? Because there is a very important concept. Artha agidea ee concept?
Yes sir.
Okay, fine. So now is this concept of stress concentration, is it a positive phenomenon or is it a negative phenomenon? ಇದು ಇದ್ರೆ ಒಳ್ಳೇದಾ ಕೆಟ್ಟದಾ? Is it a positive phenomenon or is it a negative phenomenon? Can someone speak? Am I audible?
Sir, positive.
ಪಾಸಿಟಿವ್ ಫಿನಾಮಿನನ್ ಇದು. ಯಾಕೆ?
ನೆಗೆಟಿವ್, ಇದು ಸ್ಟ್ರೆಸ್ ಕಡಿಮೆ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಸರ್.
ಸ್ಟ್ರೆಸ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಅಲ್ವಾ? ಸೊ ಸ್ಟ್ರೆಸ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಇದ್ರಿಂದ ತೊಂದರೆ ಏನು? ಸ್ಟ್ರೆಸ್ ಜಾಸ್ತಿ ಆಗೋದು ಒಳ್ಳೇದೋ ಕೆಟ್ಟದ್ದೋ?
ನೆಗೆಟಿವ್.
It is a negative phenomenon. What will happen? Because just give me a moment. The system is not properly behaving. So basically, what will happen if the magnitude of stress increases? The moment the magnitude of stress induced crosses the material property, that is the material strength whenever that happens, the material will fail. ಹೌದಾ? The material will no longer be capable of taking up the load. So thereby rendering the component unstable. ಹೌದಾ? Component fail ಆಗ್ತದೆ. Right? So that is the reason why stresses are to be contained. They should be restricted to a reasonable value. If the magnitude of stress increases, what will happen? If the magnitude of stress increases, what will happen? The component will fail. Right? That is one of the most tragic part whenever the stress induced in the component increases. So thereby, we should always take care that the stress induced in the component should be within reasonable limits. So this phenomenon of stress concentration is not a positive phenomenon. So as long as possible, this phenomenon should be avoided. Now, but there is a problem. What is the problem? So whenever you are designing any component, it is quite impossible to design the component so that it is not having any change in cross section. It is a highly impossible task to design a component which is not having any change in cross section. So suppose, is my screen visible now? Is my screen visible?
Yes, sir. Yes, sir.
Okay. So suppose you are trying to design a plate, right? So you take the case of this machine wise. When you are studying this computer-aided machine drawing, you had developed a 3D model of a machine wise. So there you had a plate, right? You had a plate which was supposed to supply the lubricant or the oil for the proper screwing and unscrewing of the lead screw. ಹೌದಾ? ಸೊ ಈ ತರ ಒಂದು ಪ್ಲೇಟ್ ಡಿಸೈನ್ ಮಾಡಿದ್ರಿ ಒಂದು ಕಾಂಪೋನೆಂಟ್, ಜ್ಞಾಪಕ ಇದೆಯಾ? ಸೊ ಇಲ್ಲಿ you assume that this is the same plate that you had encountered there. Now what is this hole representing? This hole is basically required for applying lubricant to that screw. Now what will happen if there is no hole? If there is no hole, lubricant cannot be put into the lead screw, which will damage the screw itself. It will damage both the vise as well as the screw because of excessive relative motion. There will be excessive friction. In the absence of lubricant, it will lead to wear of the component. Now this is a very difficult task. So what we will do, there we have got no other option rather than having a plate which is having a hole drilled at its center. Now what will happen here in this case? Whenever the stress lines are going here, the stress lines are supposed to cross this component this way. So here there is an increase in cross section. Here there is an increase in the magnitude of stress, which we call as stress concentration. Right? Now we can design the plate in such a way that we can minimize, if not omit completely, if not make it obsolete, we can minimize this effect. So we should always minimize stress concentration. Now how do we do it? We have a couple of illustrations. Suppose you consider the same plate where the stress induced in this highlighted region is very high. So rather what I will do, I will consider another plate. I will take a plate. Okay. Ideally, we only need to have a hole at the center of the plate. Now instead what I will do, I will drill a couple of holes here in a very symmetric manner. I will drill a couple of holes here. Now what will happen? The stress lines will not get concentrated here. Rather, since there is no material here, it will easily diverge. Thereby reducing the effect of stress concentration. As you can see, the magnitude of stress is very high here. But whereas in this case, by drilling a couple of holes more, we are trying to diverge this stress concentration. Suppose you consider, let me define stress concentration factor now. You consider as plate like this. Let me illustrate it with a numerical example. Now, you assume that these two plates are similar. Okay, they are the same plate. So first I will take this plate whose cross-sectional area is say 100 mm square. The cross-sectional area of this plate is 100 mm square, right? Now, this plate is subjected to a tensile force of 100 newtons. This plate is subjected to a tensile force of 100 newtons. Now, what will happen? The stress induced in the component now is 1 MPa. That is 100 newtons by 100 mm square. It is 1 MPa. Now, cross-sectional area andreno, ee plate na side inda nodidaga, this plate is rectangular in nature. So, this breadth into this length is what is the cross-sectional area. Ee cross-sectional area 100 mm square ಇದೆ. ಹೌದಾ? ಬಟ್ ಈ ಪ್ಲೇಟ್ ಅಲ್ಲಿ ಏನ್ ಮಾಡಿದೀನಿ, ಯು ಅಸ್ಯೂಮ್ that the diameter 50 mm. You consider the diameter of the hole to be 50 mm. Now, what will be the cross-sectional area? Idana side view alli nodidre hege kanutte. If you look at this plate from the side, there is a rectangular section of the plate. Correct? Ee portion alli correct agi there is a hole. Ee portion alli correct agi there is a hole. Right? So this is the solid portion of the plate, whereas this is the hole. Right? So let us assume by drilling this hole, the area is reduced to 50 mm square. Let us consider, but that by drilling this hole, I am considering the plate, I am drilling the hole of 50 mm diameter to the same plate. Now by drilling the hole, let us consider that the area is 50 mm square. Now what will be the stress induced? Now the stress induced is 2 MPa. Now the stress induced is 2 MPa. Now this value of stress, the value of stress where there is no change in cross section, or in other words here, if you consider the plate, let me mark this, call this as region A. Call this as region A. Region A alli there is no hole. Now you consider this green colored region and call it as region B. Okay, call this region as region B. So region A alli there is no decrease in material, but in region B there is a hole which is creating decrease in material. So we increase this stress induced in the. Now this stress, the magnitude of stress, nominal stress, we call it as nominal stress. How do we define nominal stress? Nominal stress is defined as that value of stress where there is no change in cross section. This particular value of stress is nominal stress. Wherever
Sir, not audible.
ಬ್ರೇಕ್ ಆಗ್ತದೆ
decrease in cross sectional area of the body, wherever there is a decrease in cross sectional area of the
Sir, ಏನು ಕೇಳಿಸಿಲ್ಲ.
body, there is no material to support the load. Now this value of network ಇದೆ.
Sir, voice break ಆಗ್ತಿದೆ.
Guys, just give me a while. My connection has been lost. I have logged in both from mobile as well as the laptop. Just give me a while. I will be back. Okay, can you guys hear me now?
Yes, sir.
Okay, fine. Can you also see my screen?
Sure.
Okay, fine. Now, ಸೊ ನಾನು ಇಲ್ಲಿ ತನಕ ಹೇಳಿದ್ದೇನೋ ಕೇಳಿಸ್ಲಿಲ್ವಾ? ಇದನ್ನ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ಬೇಕಾರೆ ನಾಮಿನಲ್ ಸ್ಟ್ರೆಸ್ ಮತ್ತೆ ಮ್ಯಾಕ್ಸಿಮಮ್ ಸ್ಟ್ರೆಸ್ ಡಿಫೈನ್ ಮಾಡಿದ್ನಲ್ಲ?
ಇಲ್ಲ ಸರ್, ಇಲ್ಲ ಇಲ್ಲ.
ಇಲ್ಲ ಸರ್ ಕೇಳಿಸಿ.
Just give me a while. I will read out again. So let me consider a plate like this, right? I hope I am audible now.
Yes, sir.
Okay. So consider a plate like this, which is subjected to a tensile force. This is subjected to a tensile force, say of magnitude 200 newtons in the unquad. This plate is subjected to a tensile force of magnitude 200 newtons. Now, the cross-sectional area of the plate, if when viewed from the side, okay, right? So consider this to be 10 mm thick. Consider the plate to be 10 mm thick. Fine. Let the length of the plate, or in this case the width of the plate, be, sorry, 100 aita one nimsha. This is 10 mm thick, and say this is 100 mm wide. Okay, you consider the force to be 2000 newtons, that is 2 kilonewtons. Now, what will be the stress induced? Sigma is equal to F by A. Now, what is the area of cross section? The cross sectional area is 100 into 10, which is 1000 millimeter square. So thereby, this is 2000 divided by 1000. The stress induced here is 2 MPa. Correct? Now the stress induced is 2 MPa. Now what I will do, I will drill a hole of 50 mm diameter at the center of the plate. Okay, I will consider the same plate. With the same force applied, I will drill a hole whose diameter is 50 mm. I will drill a hole whose diameter is 50 mm. Now what will happen when it is viewed from the side? Here, since I have drilled a hole, there is no material to take the force here. Now this is what the component would look like. This is what the component would look like. This is the hole, right? This portion is having a hole. So this is 50 mm. Now what is the area of the material that is available to take up the load? In the previous case, the area was 10 into 100 mm. So but here the thickness is remaining the same. But what about the cross-sectional area? 100 mm material plate is there, but adರಲ್ಲಿ 50 mm hole ಇದೆ. So now what is the area that is available to take up the load? Now the area that is available to take up the load is just 500 mm square, right? The area that is now available to take up the load is just 500 mm square. So basically ಏನಾಯ್ತು, ಈ ಒಂದು ಪೋರ್ಷನ್ ನ ಮಾರ್ಕ್ ಮಾಡ್ಕೋತೀನಿ. I will consider this portion as cross section A, right? Here there is no hole present, so thereby there is no loss of material. But whereas in this red colored line, in this red colored region, that is, let me call this as cross section B, in this particular region there is a hole which is drilled into the plate. Thereby the area at this particular region is restricted to 500 mm square. Only 500 mm square of area is available to take up the force. Now what will happen? The stress induced, this is stress induced at point A or region A to be precise. Now the stress induced at region B is given by the same force is acting, which is 2000 newtons, but the stress but the area that is available to take up the force is reduced by 50%. So thereby the stress induced at point B, what is the magnitude of stress induced at point B? Here this is 4 MPa. Now what is sigma B? Sigma B is the stress induced where there is a hole, but whereas the sigma A is the stress induced where there is no hole, right? So this particular region which I am highlighting in green is called as the nominal region. Thereby this value of stress is called as nominal stress. This value of stress is called as nominal stress. Whereas whenever there is a change in cross section of the body, the stress will be very high in that particular region. Well, that is obvious. The stress will be very high. So thereby this value of stress is called as maximum stress. This value of stress is called as maximum stress, which is denoted by sigma max. This value of stress is represented by sigma norm. Sigma norm stands for nominal stress. Sigma max stands for maximum stress. So ಅರ್ಥ ಆಗಿದೆ ಇದು ನಾಮಿನಲ್ ಸ್ಟ್ರೆಸ್ ಅಂದ್ರೆ ಏನು, ಮ್ಯಾಕ್ಸಿಮಮ್ ಸ್ಟ್ರೆಸ್ ಅಂದ್ರೆ ಏನು ಅಂತ ಅರ್ಥ ಆಗಿದೆಯಾ? Is this concept clear?
Yes, sir.
Okay, fine. Now, if we take the ratio of maximum stress to nominal stress, if we take the ratio of maximum stress to nominal stress, this ratio is called as stress concentration factor. This ratio is called as stress concentration factor. Now, in the examination, they might ask you the definition of stress concentration. What is stress concentration? Stress concentration is the localization of stresses due to abrupt decrease in the cross-sectional area of the body. This is how you define stress concentration. If they ask you the definition, of stress concentration factor, then the stress concentration factor is defined as the ratio of maximum stress to nominal stress. This is what is meant by stress concentration factor. So ಅರ್ಥ ಆಗಿದೆಯಾ ಈ ಕಾನ್ಸೆಪ್ಟ್? ಅರ್ಥ ಆಗಿದೆಯಾ? Is the concept clear?
Yes, sir.
I want someone to respond. Am I audible?
Yes, sir.
Okay. Do you guys now know the difference between stress concentration and stress concentration factor? ಅರ್ಥ ಆಗಿದೆಯೇನ್ರ?
Yes, sir.
Okay, fine. So now, let us move on. In the previous example here, I have shown you one way of reducing or minimizing stress concentration factor. What I am trying to do is, now I am trying to reduce the stress concentration or the stress concentration factor. Problem exam alli eradu tara kelbodu. They might ask you to discuss the ways or methods of reducing stress concentration or ಕೆಲವೊಮ್ಮೆ stress concentration factor ಅಂತಾನು ಕೇಳ್ತಾರೆ. So one way, whenever there is a hole which is drilled within a plate, by drilling additional holes, so basically ನಾನು ಏನ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಇಲ್ಲಿ, ಈ ಹೋಲ್ಸ್ ನ ಡ್ರಿಲ್ ಮಾಡೋದ್ರಿಂದ ಸ್ಟ್ರೆಂತ್ ಆಫ್ ದಿ ಪ್ಲೇಟ್ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತಾ ಇದೆಯಾ? Strength of the plate increase ಆಗ್ತಾ ಇದೆಯಾ? ಇಲ್ಲ, because I am removing the material. It does not mean that the strength of the plate is increasing. Whenever I am drilling additional holes, ಏನಾಗ್ತಾ ಇದೆ, ಸಿಂಗಲ್ ಹೋಲ್ಗೆ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ the stress concentration is decreasing. So this is one thing that you should remember. So one of the first method of reducing stress concentration is drilling additional holes. Just give me a while. Drilling additional holes will help to reduce the stress concentration. Then if you look at the example that I had considered previously, here if you see, there is no fillet or notch present. ಹೌದಾ? ಈ ಸರ್ಕ್ಯುಲರ್ ಏರಿಯಾದಲ್ಲಿ as you can see, there is no fillet or notch present. ಸೊ ಬೇಸಿಕಲಿ ಏನಾಗ್ತಾ ಇದೆ, ಲೈನ್ಸ್ ಆಫ್ ಸ್ಟ್ರೆಸ್ ಈಗ ಬಂದು ಇಲ್ಲಿ ಅಕ್ಯುಮುಲೇಟ್ ಆಗ್ತಾ ಇದೆ. But you see, whenever there is a fillet like this, whenever there is a fillet, ಅದು ಬಂದು ಒಂದು ಕಡೆ ಕಾನ್ಸಂಟ್ರೇಟ್ ಆಗಲ್ಲ, it will easily flow through. So whenever you have to have a sudden change in the diameter of the shaft, it is always advisable to give fillet, right? Then the next technique, so basically ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಈ ಲೈನ್ಸ್ ಆಫ್ ಸ್ಟ್ರೆಸ್ ಇಲ್ಲಿ ಸಡನ್ ಆಗಿ ವಿ ನಾಚ್ ಬಂತು. This is a very commonly encountered machine element, which is a screw. So ಇಲ್ಲಿ because of sudden presence of this thread, the stress will get concentrated here. But ಇಲ್ಲಿ ಏನ್ ಮಾಡಿದ್ದಾರೆ, to avoid that, additionally ಒಂದು undercut ಕೊಟ್ಟಿದ್ದಾರೆ. So this undercut will help to ease out the concentration of stress here. ಅಥವಾ ಏನ್ ಮಾಡಬಹುದು, I can completely remove the diameter here. ಇದು ಪೂರ್ತಿ ಇದು ಮಾಡಿದ್ರೆ the effect of stress concentration will be reduced. As you can see here, there is a reduction in diameter, right? Then if you look at this example, this is what I was speaking earlier. So ನಾನು ಇಲ್ಲಿ green colored region ಅಲ್ಲಿ highlight ಮಾಡ್ತೀನಿ, that is good. So ಇಲ್ಲಿ ಏನೋ we have drilled additional holes. Pink color ಅಲ್ಲಿ ಏನು highlight ಮಾಡ್ತೀನಿ, ಅಥವಾ say ಈ almost brown color region ಅಲ್ಲಿ this is bad, right? This is not good. Here you see sudden ಆಗಿ ಏನೋ ಕೀಸ್ ನ ಲಾಕ್ ಮಾಡೋದಕ್ಕೆ ಶಾಫ್ಟ್ ಮೇಲೆ there is a sudden keyway present. But here ಏನಾಗಿದೆ, here as you can see additional holes ಕೊಟ್ಟಿದ್ದೀವಿ, this is good. So here this is poor, ಇಲ್ಲಿ undercut ಕೊಟ್ಟಿದ್ದೀವಿ, this is good. There is a complete reduction in diameter, that is also good. But if you see here, ಇಲ್ಲಿ ಏನಾಗಿದೆ, ಇದಕ್ಕೂ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ ಈ ಪೋರ್ಷನ್ ಅಲ್ಲಿ ಹೈಲೈಟೆಡ್ ರೀಜನ್ ಅಲ್ಲಿ ಫಿಲೆಟ್ ಕೊಟ್ಟಿದ್ದಾರೆ. ಸೊ ದೇರ್ ಬೈ ಸಡನ್ ಚೇಂಜ್ ಇಲ್ಲ, there is a gradual change. This is the difference between sudden change and gradual change. ಇಲ್ಲಿ ಏನ್ ಮಾಡಿದ್ದಾರೆ, ಫಿಲೆಟ್ ಕೊಡೋದ್ರ ಬದಲು ಪೂರ್ತಿ ಚಾಂಫರ್ ಮಾಡಿದ್ದಾರೆ. So this is good, this is bad. This particular thing is bad. Okay, ಅರ್ಥ ಆಗಿದೆಯಾ? Do you know, can you guys now just elaborate on the ways of reducing stress concentration factor? ಈ ಕಾನ್ಸೆಪ್ಟ್ ಅರ್ಥ ಆಗಿದೆಯಾ? Can we go ahead?
Yes, sir.
Yes, sir.
So we'll write up on this, you don't worry. You can just go through that. The concept will become much more clearer when we encounter problems, right? Okay, so let us now try to solve a couple of problems. So ಬರ್ಕೊಳ್ಳಿ numericals on stress concentration factor. So let us consider problem 1. Okay, problem 1. ಬರ್ಕೊಳ್ಳಿ, determine the maximum stress, determine the maximum stress in the following cases. Determine the maximum stress in the following cases by taking stress concentration into account. Determine the maximum stress in the following cases by taking stress concentration into account. ಆ ಪ್ರಾಬ್ಲಮ್ ಕೆಳಗಡೆ ಸಬ್ಹೆಡಿಂಗ್ 1 ಬರ್ಕೊಳ್ಳಿ. ಸಬ್ಹೆಡಿಂಗ್ 1, a rectangular plate.
Determine maximum stress in following.
In the following cases by taking stress concentration into account. By taking stress concentration into account. Right? Case 1, a rectangular plate. A rectangular plate of 50 mm into 80 mm. A rectangular plate of 50 mm into 80 mm with a hole of 10 mm diameter, with a hole of 10 mm diameter in the center, with a hole of 10 mm diameter in the center, loaded in axial tension, loaded in axial tension of 10 kilonewton, loaded in axial tension of 10 kilonewton, full stop. The thickness of the plate is 10 mm. The thickness of the plate is 10 mm. Now this is a very commonly asked problem in your examination. This has been repeatedly asked. Such problems are very important. These types of problems will appear both in module 1 and module 2. Okay. So data ಬರ್ಕೊಂಡಿದ್ದೀರಾ ಅಲ್ವಾ? This is the data that we have listed. Now looking at this data, they have told you that the plate is rectangular in nature. Now typically if we try to draw it, this is a rectangular plate, right? The dimensions of the plate are given to be 50 mm, right? The height of the plate is given to be 50. The width of the plate is given to be 80. This is 80 mm. Now this plate has got a hole, right? The diameter of this hole is given to be 10 mm. The diameter of this hole is given to be 10 mm. And also they have told you that the thickness of the plate, this is the side view, the thickness of the plate is given to be 10 mm. Now what will happen due to the presence of this hole when we are viewing this plate from the side? The hole will be present here, right? The hole will be present here. Thereby, there is no material here. The dimension of this hole is given to be 10 mm. Now, they have told you to determine the maximum stress. They have told you to determine the maximum stress. Now, what is maximum stress? Let us try to write the formula of stress concentration factor. How did we define stress concentration factor? Stress concentration factor is represented by the symbol Kt, which is given by the ratio of maximum stress to nominal stress. It is given by the ratio of maximum stress to nominal stress. Now, how do you determine the nominal stress in the member? We will consider a cross section where there is no change in dimension of the component. Now call this as A. The stress induced at cross section A is what we call as nominal stress. That is what we call as nominal stress. Next class ಇರೋದು ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ನಾನು ಹೇಳ್ತಾ ಇರೋದು?
ಸರ್
ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ಯಾರ್ದು?
ಮಧು ಸರ್
ಇದು ಮಧ್ಯಾಹ್ನ ಏನಾದ್ರು ಕ್ಲಾಸ್ ಇದೆಯಾ ನಿಮ್ಗೆ ಇವತ್ತು?
ಲ್ಯಾಬ್ ಇದೆ ಸರ್.
ಲ್ಯಾಬ್ ಇದೆಯಾ?
ನಾಳೆ ಇದೆ ಸರ್. ನಾಳೆ 5 o'clock ತನಕ ಇದೆ ಸರ್.
ಹೌದಾ? ಓಕೆ, ನಾನು ನೋಡ್ತೀನಿ ಟೈಮ್ ಟೇಬಲ್ ನೋಡ್ಬಿಟ್ಟು ಇನ್ ದಿಸ್ ವೀಕ್ ಐ ವಿಲ್ ಬಿ ಟೇಕಿಂಗ್ ದಿ ಕ್ಲಾಸಸ್ ಡೈಲಿ. ಓಕೆ, ಬಿ ಪ್ರಿಪೇರ್ಡ್ ಫಾರ್ ಇಟ್. ಇಫ್ ನಾಟ್ ಏನಾದ್ರು ಅಕಸ್ಮಾತ್ ಬೆಳಗ್ಗೆ ಬೇರೆ ಯಾವ್ದು ಕ್ಲಾಸ್ ಸಿಗ್ಲಿಲ್ಲ ಅಂತ ಹೇಳಿದ್ರೆ ನಾನು ಮಧ್ಯಾಹ್ನದ ಸೆಷನ್ ಅಲ್ಲಿ ಕ್ಲಾಸ್ ತಗೋತೀನಿ. ಯು ಗೈಸ್ ಜಸ್ಟ್ ಬಿ ಪ್ರಿಪೇರ್ಡ್ ಫಾರ್ ಇಟ್. ಓಕೆ, ಸೊ ವಿಲ್ ಕಂಟಿನ್ಯೂ ದಿಸ್ ಇನ್ ದಿ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್. ಏನಾದ್ರು ಡೌಟ್ ಇದ್ರೆ ಯು ಕ್ಯಾನ್ ಕಾಂಟ್ಯಾಕ್ಟ್ ಮೀ ಇಂಡಿವಿಜುವಲಿ. ಓಕೆ, ಏನಾದ್ರು ಡೌಟ್ಸ್ ಇದೆಯಾ ಬೇರೆ?
No, sir.
No, sir.
Okay, fine. Okay, you can join the next class now. We shall continue this problem in the next class.
Thank you, sir.